Welcome to our CS554 project. The title of our project is the evaluation of methods to index vast amounts of data in large storage systems. My name is David O'Connor and I am working with Pak Hui on this project. In this project, we are going to evaluate methods to index vast amounts of data in large storage systems. The motivation for this is that the state-of-the-art index and query technologies are critical for large data sets we have today. In this project, we would like to explore the interaction between various indexing methods and file systems on text-based files. Some of the expectations going into this project are: the indexing time will increase when the number of files being indexed increases. Second, the query time will increase when the number of files in the index increases. And a third is a parallel distributed file system such as Lustre will index faster than a single node file system such as NFS. Our project will use the following file system test beds as part of our evaluation.
Local file system, we use desktop PCs with the following specs: Intel i5 CPU, 4 gigs RAM, and 500 gigabyte hard drives. We installed Linux CentOS 7.4 and used an XFS file system. For the Fusion FS, we spent a lot of time trying to set it up. Some of the obstacles we encountered, including libraries were missing, OS mismatch, and problems compiling the software. In the end, Fusion was partially up. However, it continually core dumped, throwing errors on the screen, file misses, missing, etc. After talking with the TA and professor, we all agreed that we should not continue with Fusion file system since there is no support. We created several test beds for our Lustre file system. The first one was the single node cluster on a PC. On this PC, we installed the Lustre server and client applications using the same PC hardware that we had during the local file system. We created a 10 gigabyte MDT partition and a 20 gigabyte OST partition for use by the Lustre file system. For the multi-node cluster on the PC, we created 2 MDTs and 7 OSTs. Each MDT consisted of the same 10 gigabyte partition, and each OST consisted of the same 20 gigabyte partition, but for a total of 140 gigabytes of storage. Due to some of the hardware limits we came across, where we did not have enough PCs, we installed the server and client applications on some of the same equipment. The final configuration we did was a multi-node cluster on a Chameleon system. This cluster consisted of 2 MDTs and 16 OSTs. From the Chameleon hardware, we used the 2 different configurations, the M1 large and the M1 medium for our servers, both MDTs and OSTs. So this file system had a total of 320 gigabytes of storage. Again, due to some of the hardware limits on Chameleon and number of servers we could use, some of the Chameleon devices were doing server and client applications. For all of this, we used Lustre version 2.10.0. What we noticed with Chameleon was that there was contention with other students for Chameleon resources and being able to create instances. We also saw some slowness, which was one of the reasons we wanted to set up the other test beds. We also, while we were creating some of the files, we also ran into an inode issue, specifically when we were creating the 1 million 1K files that you'll see later on in the presentation. So in order to get around that, we had to increase the number of inodes, and even though the number of disk space was low, like 3%, the inode users was 31%. The next few slides are some pictures of our Lustre testbed topologies, along with some background Lustre information. For our Hadoop file system testbed, we created a single node cluster on a PC using the same hardware as the local file system PC. We created a 10 gigabyte name node partition and a 20 gigabyte data node partition. For the multi-node cluster, we created one name node and 7 data nodes. Partition sizes were the same as the single node cluster with a total data node size of 140 gigabytes. We use Hadoop version 2.7.4 for all the installations. One limitation we had was the number of physical PCs that were available. Because of this, we had to install multiple file systems on each PC, for example, Lustre and Hadoop. We noticed PC performance issues when the Hadoop application was running, even though no files were being written. We will need to further investigate to quantify and evaluate this. We were also not able to use the Fuse libraries to mount a HDFS drive to allow direct access from the Linux file system. We had to rely on the Hadoop commands such as Hadoop FS to read and write files to and from the Hadoop file system. We did notice that transfers were slow when we were transferring the 1K files. We were seeing transfer rates of about 24,000 files per minute when we were transferring the 1 million files that are part of our setup. We partially installed a Hadoop cluster on Chameleon, but stopped due to issues we had run into with Chameleon earlier. The final file system testbed we used was NFS. We set up one NFS server connecting to 6 clients. The NFS server was running NFS version 4 and consisted of a 50 gigabyte partition. The clients mounted the NFS server via the built-in Linux commands. This was by far the easiest setup due to the commands being part of the Linux operating system, compared to Lustre and Hadoop, which required separate packages.
This is Pak Hui. I'm going to continue the presentation, start with the information retrieval libraries. There are several existing information retrieval libraries, such as the Lucene, C-Lucene, Sapien, Llama, etc., Cyprian available. So our team investigated this technique and found out that the most common field, Lucene, of course, is the full text search library in the Java-based, and Sapien is like Lucene, but it is a C and C++ based. So the integrated with the C++ application will be easier. And we also tried the Llama, which is a tools kit designed to facilitate the research in language model information retrieval, and it's very, very flexible to use for any application. So once we have this indexing and the retrieval in place, we are using the following measurement. The main key thing is the indexing time, which is the size of the index per second. In unit, it will be the byte per second. And the query time, which defines the query per second. So we got some surprising result we just found out in the later slide. To use the tools library, we are using the existing tools like the Solar, which using the Lucene library, the Java-based, and Recall is an Experian library, is a C++ based, and Integrate is a Llama, using the Llama library, is a C++ based. It's a command line based tools. So once we have these tools set up for evaluation, we are going to run the Linux grep as a comparison of this data retrieval, and hopefully later on we have stabilized our Hadoop setup. We're going to use a Hadoop grep as a comparison also. And data preparation is a big part of what we do. So one of the goals is to have a standardized data set. So we will have a various text file size text file. For example, 1 gigabyte text file, a big one, and 1 megabyte, 10 kilobytes, and 1 kilobyte text files. So how do we generate this file? So we first start with the one big 1 gigabyte text file. After that, we're using the split command, run some script to break it down into 1 meg, 10K, 1K file size. For example, we have one big 1 gigabyte file, text file, and then 1,000 1 megabyte text file, and then 100,000 10K byte file, and then 1 million 1 kilobyte file. So the content will be the same, so it won't be any delta there, and that will be our data set. And all this data, when you generate it, will be put into the different file systems, such as a local node, NFS, and Lustre NFS. And the word retrieval, we will find some word common and uncommon keyword, like the word God will appear everywhere. Superman will not be that often. And the following test or evaluation we do, we will at least run it 5 times and take the average out to see if we can get a consistent result. And the content of the data we obtain is from the two way to do it. One is from the we got it from Project Gutenberg, which got a free ebook. They are not a dictionary. That means the text is more evenly distributed. And we're going to run the dictionary like text file. That means that a file has every single word inside the file. And the following data set we're going to show it comes from the Project Gutenberg, also on the test bed we described earlier. What you're looking at is the test result from Limmer. You can see that the left-hand side we have 1K file size, 1 million file, 3 times because we have 3 different file systems, local node, NFS Lustre. The same test repeated on the 10 kilobyte file size with 1,000 file, and 1 megabyte 1,000 file on the 3 different file systems. You can see the indexing when you go to the 1 meg file, pretty fast. It's like a few minutes. When you go to a 10K file size, the indexing time increase a lot, except the local node. But it goes to the 1 kilobyte file size, the 1 million file, the index. You can see that the worst case in the Lustre file system takes 7 hours to index all these files. And the column next to it, index throughput, is the how much time we just divided by by 1 megabyte files. So the result is a byte per second. So the worst case is 38 kilobyte per second. The fastest we have 6.7 megabyte per second. And the thing we found out is that the retrieval time is always less than a second. I think we learned from our experience is that maybe 1 gig total file size probably not going to be good enough to see a difference in the retrieval time. The indexing by the worst case scenario injury using Lustre file system did not get slowed down versus time. So this is what we're hoping for. We're worried about that. Maybe going fast at the beginning and slow down, and turns out that's not the case. And the next one is the other indexing tools I explained. Same task will run with a 1 kilobyte file size, and then 10 kilobyte file size, 1 megabyte file size, different file number of files and different file systems. And then similar result we found that is that it's not as fast, but for the 1 megabyte file size is consistent or between 3 different file systems. And then we can see the difference when we're running into the 1 kilobyte file size, 1 million file. Lustre, again, it takes hours to even index the 1 million file. And then we run the Lucent similar testing, and then 1 kilo, 10 kilo, 1 megabyte files, and then similar result we are seeing. And this is a comprehensive look between the 3 indexing tools and different file system versus different file size. So the left-hand side is the 1,000 kmin 1 megabyte files, and all across they are like very consistent. They're the fastest ones. So that means that it's really the number of file causing the slowdown of the indexing, not the file size. And you can see that the performance of one case worse across the board. We are doing other couple interesting experiment. For example, the graph. We see that, hey, how can I does it affected by the number of file also? Lustre system, the graph is also really slow, and again is slowing down once have more file. We also did an experiment in running like a 10 instance of the same indexing system because we want to stress the system to see where the bottleneck of the system. And you can see that between Lustre and NFS, Lustre take a few times more to index the same amount of file compared to NFS, even if the 10K file size. So in a preliminary observation, we have that number one, the retrieval of our data set is not good enough to tell the difference for each retrieval. So we probably need a bigger file to index. So in general, in our case, NFS is faster than Lustre, which could be the CPU and memory limitation. We're going to do further study on that. And when using Lustre with Solar, the Lucent, there's a lot of variation with the indexing. Sometimes take a few hours, sometimes take a whole day. Again, we need to look into that. And none of these tools we mentioned about can do the 1 gigabyte file system. So it always crashes when we run the tools. So that's why we don't see the result earlier. And problem we face when we do indexing is originally planned to include the C Lucent. It turns out that the tools we can download is not too unstable. It couldn't do a big file, it couldn't do a larger number of files. And also the grep command by itself were not able to take a millions of a file, so we had to combine the find command to do that. And in the remaining work, we're going to do is stabilize a Hadoop file system when used different data set like a dictionary type of library, and set up impairment to limit the internode bandwidth to simulate the WAN environment. It may help to show the performance difference between the NFS and Lustre file system. And that's conclude our presentation. Thank you for watching it.